Thanks for checking out our screencast about how to design a microfluidic device using Solidworks. Before we get started, a quick bit about us here at Parallel Fluidics. We are a rapid manufacturer of microfluidic devices. We can turn around custom parts in as quickly as 3 days in the same materials and design guidelines that are required for high volume production. This allows you to iterate super quickly through the development process and get to a scalable design as fast as possible. If you have a device that you'd like to quote, you can just head to parallelfluidics.com and upload your CAD file. We'll get back to you with a configurable quote where you can adjust lead time, quantity, and expedite to best match your needs. For the exercise today, we'll try to design a fairly simple microfluidic droplet generator. If you aren't familiar with the concept, they are a type of device that allows you to make an emulsion of nanoliter-sized water droplets suspended in an oil carrying fluid. It's an extremely important type of device that's used across the life sciences for many different applications. All right, let's jump into the device design process. First things first, it's always a good idea to lay out a schematic of your device on paper before we start designing in CAD. This device will be a cross-style droplet generator. Let's start by sketching a basic cross in the center of the page. We know that we'll have fluid coming in through the right channel, the center channel, the left channel, and then exiting through the bottom. Oil will be coming in through the side inlets, and water will enter through the center of our nozzle geometry, which we'll later design in CAD. The water and oil will combine in the nozzle and send droplets out through the exit. Now, we know that we want a little bit of fluid resistance leading into the cross junction, so we end up with the proper flow rates at reasonable pressures. I'll just represent that by drawing a little fluidic resistor in the center. And the same thing on the side channels. I'm not a great artist, but that's okay because this is just a schematic representation of the device that we'd like to make. And it's going to make our lives a lot easier when we do make the jump to CAD. Okay, we have our nozzle, inlets, and resistors. Now we need to think about how we are going to actually get our fluid into this device. We'll represent a tube fitting with a circle that comes in the middle of the channel there. Then for the oil outlets, we'll just tie those together to their own tube fitting at the top of the device. And finally, we just need to collect our droplets from the outlet channel with another fitting. Okay, so we've laid out our device. Once again, we have water coming in through our tube fitting in the central channel, which goes through the fluidic resistor and into the cross junction. And we have our oil inlet, which will split into two channels that then come into the side of our cross junction geometry. The droplets will form in the nozzle and then will flow into the outlet channel and out of the device through a final tubing fitting. Now that we have our device designed on paper, we are ready to make the transition into CAD. But before we get started in SolidWorks, we have a couple tools available that can make the design process easier on our website. Let's open a browser window and head to parallelfluidics.com. This will bring you to our homepage, but we have a whole section of the site dedicated to helpful resources that we call the Design Portal. You can click the button here to check it out. In the portal, there are a few different sections. The design guide has detailed info about what is and is not possible in our manufacturing process here at Parallel. The knowledge base has other articles, webinars, and screencasts about microfluidic design. And the component library is a collection of embeddable components that help solve some of the typical engineering challenges in microfluidic design. We'll explore this area in more detail later, but inside you'll be able to find options like tubing ports, reservoirs, and adapters. Our core formats are a set of standardized CAD templates that speed up the design and prototyping process. If you design your device using one of these formats, it guarantees that it will be compatible with the components that I mentioned, and will also upgrade your orders to a 1-week lead time for free. If we scroll down the page, there's a little more info here. Then we get to the 3 different size options for the core formats. Let's choose a microscope slide format for the device that we will design today. If you click the Download CAD Template button, you should automatically have a Parasolid file land in your Downloads folder. Most modern CAD systems should recognize Parasolid files, whether you are using SolidWorks, Fusion 360, or some other package. Now we can head over to SolidWorks and open up the CAD template that we just downloaded. I'll choose a metric document format because that's how my brain works. In our template here, we can see that we have 2 bodies that automatically get opened in our part. The blue layer that you see is what we call the fluidic layer. This is the body that we'll model our channels and features into. Underneath the part, we can see the green cap. This will be the layer that will seal our device geometry. Before we go any further, let's save our work. I'll call it My Device. Let's hide the cap and create a sketch on our top plane. We'll start the CAD model with the cross-junction region, since this is the most critical area of our design. I'll zoom in a bit because we're going to make some pretty small features here. Speaking of which, before we begin, it might be a good idea to review some design guidelines to make sure that our device will be manufacturable from the start. Let's pop back over to the Parallel Fluidics website, hover over Design Portal, and select Design Guide. When we expand the manufacturing guidelines in the table of contents, we can see design topics. If we select any one topic, it'll bring us to a section of that page with a quick description and some design rules. Let's choose Feature Dimension. This shows us a cross-section view of a microfluidic channel and calls out some minimum and maximum values. I want mine also to be small, but to be within guidelines, so I'll choose a nominal 100 by 100 micron cross-section. We can often produce devices outside of these guidelines, but if you can stay within them, it will reduce the cost and risk associated with making your prototypes. For the sake of time, we won't look at the guidelines for every feature today, but it's a good idea to familiarize yourself before designing real parts. Okay, now we'll go back to CAD. The first feature we will sketch is the nozzle with the 100 by 100 micron cross-section. Obviously, the dimensions would need to be changed for your particular needs, but this is just an example for us. I'll create a center line as a reference. Make a construction geometry. Sketch a corner rectangle. And then make it symmetric about that center line, coincident with the origin. Make this 100 microns wide, because that's what we want for our channel width. And temporarily, we'll just make it 400 microns long. Okay. We can then extrude cut down 100 microns into the part because we want the channel to be as deep as it is high. I have to flip the direction of my cut and set the dimension here to 100 microns. From here on out, we'll make the depth of all of our features 100 microns. We can also rename the extrude cut feature to nozzle so that our feature tree stays nice and organized. Now we can sketch the channel that will bring oil into the horizontal part of the cross junction. We'll create another sketch on the top plane. Draw another center line. Make it construction geometry. And another rectangle. We'll make the bottom of the rectangle coincident with the origin. Make it symmetric. Then apply dimensions of 200 microns in width. 500 microns in length. Finally, we'll extrude cut up to the surface that we made earlier. Let's rename the feature to oil entry. Same deal here for the top channel. Create a sketch on the top plane. Create a vertical center line. Make a symmetric rectangle. Make the bottom of the rectangle coincident with the top of our previous channel. Keep the width 200 microns. And the length 500 microns. Extrude cut up to the same surface. And rename the feature to water entry. Now let's model the outlet using the same workflow. Okay, pretty good so far. We have our cross junction started. Our water channel comes in from the top, and our oil channels come in from the side, and both combine through nozzle and flow through to our outlet channel. Now that the core geometry is in place, we can start to think about how the rest of the device will be laid out. It's important to consider things like inlets and outlets early in the design process to make sure that we can fit into our chosen template. Let's go back to the Parallel website to check out our connector options. We can hover over Design Portal on the nav bar, and then choose the component library. This will bring up a few different components that we can use to interface to our tubing. Let's choose the quarter 28 port, which is a threaded component that can be used with capillary tube fittings like those from IDEX. We also include links to some compatible fittings and tubing, just so it's a little easier to get your experiments up and running. Let's click the Download CAD Model button to get a Parasolid file, and then open it up in Solidworks. Now we can refer back to it if we need any more information. Quick side note here, all of our components at Parallel are typically designed for a minimum of 9mm spacing between each other. The same spacing is used in a 96-well plate. It's important to note that you also need to think about the third-party connectors you are going to use with the port when laying out spacing. For example, if you picked a threaded fitting with a big screw head, you'd need to account for that at this stage of the design process. Let's hop back into the main device design and lay out our vias, or our through holes that will connect our channels to the port on the top surface of the device. We can create a sketch on the top plane again, and drop in another vertical center line. We know from our hand sketch that we need 2 vias above the cross junction and 1 below the outlet. Let's drop 3 circles right on the center line. Since we know our components at Parallel are designed for a minimum of 9mm spacing, we can add a 9mm dimension to one of the circles to give us a visual gauge. We can then use an equal relation to make sure all of the circles are the same size. Let's add a couple of dimensions to put the port locations in roughly the right spot according to our hand sketch. We'll choose 30mm for the 2 furthest ports and 18mm for one in the center. Then we can rename the sketch via locations. It will serve as our reference as we design the rest of our channels. The next features to add are the serpentine fluidic resistors that we sketched out in our schematic. First, we'll create another sketch on the top plane and drop in a vertical center line. For this channel, we'll use a thin extrude feature instead of sketching the whole channel profile. To do that, we sketch a few horizontal lines. Then we'll connect them with tangent arcs, making sure to create a tangent relation between each arc and its corresponding line. We'll select each arc, add an equal relation, and then a symmetric relation between the endpoints of the horizontal line and the center line. We'll add dimensions to make the spacing between the channels and between the center points of the arc. Finally, a 4mm dimension between the lowest line and the origin. These sketched lines will serve as the center of our thin extrude feature. Exit the sketch and click Extruded Cut, and select the thin feature box. Set direction 1 as up to surface and select the bottom of our previously formed channels, and deselect direction 2. You may have to toggle flip side to cut to get the feature to cut in the correct direction. Set the thickness to 200 microns and the type to midplane. Finally, hit the check mark and rename the feature to Serpentine. It's a bit of work to create and dimension serpentine features, so whenever possible, we want to use patterns to save us both time modeling and to help capture our design intent. Let's make a linear pattern of our first serpentine. Select the linear pattern feature, then select the y-axis as direction 1. The pattern spacing should be 2mm to match the center-to-center distance of our initial serpentine. To make this even more parametric, we could use equations to link the spacing back to the original sketch, but that's a little outside of the scope of this tutorial. That looks good, so we can confirm the pattern and rename it to Serpentine Linear Pattern. Now we just want to replicate this pattern for the 2 oil channels. Linear pattern can be our friend again here and save us some work. Select a new linear pattern feature, select direction 1 as the x-axis, set the spacing to 7mm and the number of instances to 2. This will replicate the pattern on one side, but we want to create both. To do so, we can click into the box for direction 2, select the x-axis again with the same parameters, and flip the direction. We should also select pattern seed only in this case, since we are using one axis for both directions. Finally, make sure both Serpentine and Serpentine Linear Pattern are selected. Confirm and rename to Serpentine Copy. Looking good. Our most critical geometry is now in place. We just need to connect up the features with our remaining channels and adjust a few more details. Let's connect the center serpentine to our via location and the water inlet using some simple extruded features. Okay, let's use thin extrudes to add the rightmost channels, making sure all the channels are named appropriately. Now let's mirror the last set of features about the right plane to save us a little work. We're starting to get quite a few features in the tree, so let's also dump all of the inlet features into their own folder to keep things neat. We'll use another extruded cut to connect the outlet to the bottommost via position. Great, all of our channels are in place. Let's move on to the vias. In our process of parallel, we drill all of the through holes after the molding process. To start, we can add a simple through hole centered at each position. We'll choose a 500 micron diameter for one circle, and then make all of them equal and make sure to extrude them all the way through the part. A lot of customers who upload parts to our website leave their vias in this state. One of the big risks with machining is that sometimes tiny burrs can be left behind at the channel interface, potentially causing flow issues. We'll add a couple more features to help prevent burrs and improve alignment during the drilling process. Let's create another sketch with circles centered on each via hole. Then select one of the circles and add a dimension of 125 microns between it and its respective via hole. We'll then extrude cut this feature down to the channel surface and name it via extension. Create a new sketch, but this time, let's put the sketch plane on the channel surface. Then select the sketch from the via extension feature and click Convert Entities to capture the same geometry. We'll extrude cut this sketch through all, making sure to set the included draft to 45 degrees. Press confirm and we should have a nice smooth cone connecting the via hole to the channels. Creating this conical interface both reduces the chances of burrs and prevents them from blocking channels. We recommend this type of interface for all vias as part of our design for manufacturing feedback here at Parallel. Let's rename the feature Via Taper and put all of the via related features into a folder. Now our device is looking just like our schematic. We aren't quite done yet though. We need to make sure that our device fits within manufacturing guidelines. Specifically, we have a bunch of sharp corners in this device that aren't manufacturable in mold-based processes. Corner radii are covered in another section of the design guide, but as a general rule of thumb, we want to avoid small radii as much as possible. Smaller radii require smaller tools in the manufacturing process, driving up the cost of mold fabrication. Let's go add fillets to our external corners first. We'll select the fillet feature, set the radius to 500 microns, then grab all of the external corners except for in the nozzle region. We'll also do the internal corners and make them a 700 micron radius so that the channel stays a consistent width throughout the curved regions. We'll add a 100 micron radius fillet to our nozzle zone, since this is our most critical geometry. Finally, we'll add a 500 micron radius fillet to all the via corners, and then place all of the fillet features into their own folder. The last feature that we'll add to the fluidic layer is some draft. Draft is a slight taper of the channel walls that allows the part to eject from a mold without damage. For this part, we'll add 2 degrees of draft around the entire channel perimeter by selecting the draft feature, specifying the channel surface as the neutral plane, and then right-clicking on a channel face and choosing Select Tangency. This should grab all of the tangent faces, but sometimes it doesn't work perfectly. If any of the channel faces weren't selected on the first try, you can right-click on them and choose Select Tangency again. Continue this process until all of the channel sidewalls are highlighted, then hit Confirm. Alright, fluidic layer work should be done. It's worth a quick check to make sure all of the corners were filleted and the draft worked correctly. A great tool that Solidworks has in the Evaluate tab is called Draft Analysis. If you select the surface of the device and adjust the angle to 2 degrees, it will color code the surfaces, showing you which have at least 2 degrees of draft. This really helps to verify that all of your microfeatures are drafted appropriately. Since the vias and sidewalls will be post-machined in this case, it's preferred to leave them undrafted in our process. All we have to do now is create our final assembly and add the ports. We'll select File, New, and then choose an assembly. If we click Insert, highlight our device, and then hit the green check mark, it will automatically drop the new part into the assembly with the coordinate system fully aligned. Now we can also drop in the ports by selecting Insert again, highlighting the port, and then clicking in the model space. This will leave the part floating so that we can use mates to align it to the proper via hole. Let's do that by selecting mate, and then grabbing the inner diameter of the hole in the bottom of the port, and finally selecting the inner diameter of the via. This should automatically generate a concentric mate. Press the green check in the pop-out window to confirm alignment if it looks good. Now the part is aligned in XY, but we need to add a mate in Z. Let's drag the part away from the fluidic layer and add a mate between the bottom surface of the port and the top surface of the fluidic layer. The position of our port is now set. Let's repeat the process for the remaining ports. Alright, all the ports are now in place. Let's show the capping layer that we hid at the beginning of the exercise by expanding the fluidic layer in the feature tree, right-clicking on the solid body, and pressing the eye icon to show. Okay, now our CAD is all wrapped up. We've got a solid design that matches our original schematic and is ready for manufacturing. Now, all we need to do is actually get it fabricated. The process to submit a part like this for quote is super simple. All we have to do is export the whole assembly as a step file and upload it to the Parallel website. To do so, just click File, Save As, and then select Step AP214 as the file type. Click Save, and SOLIDWORKS will export the file to the selected folder. Now we just toggle back to the Parallel website and hit the big Upload button in the top right corner of the screen. Drag your device over to the upload zone and enter in your desired quantity, material, and cap option, or any other notes about your design. Then just click the Submit button and we'll send you a configurable quote and design feedback in less than a day. Here's an example of what a quote would look like for this design. Since we did a good job of following the guidelines, the part doesn't require any changes. If there are any problems at this stage, this is where we would flag them and provide necessary feedback. We can usually accommodate small modifications without requiring a new CAD upload. But if there's anything major, we'll give you feedback that will help you to arrive at a workable design. On the lower part of the page, we have the options to configure your quote. You can slide the quantity, select your device material, and your capping method. All of the pricing will update in real time, and you can click and drag your CAD model to make sure everything looks as expected. Select the lead time, add the parts to your cart, and you're ready to place your order. This process is by far the fastest way to go from concept to functional microfluidic prototypes. That's it. Please reach out if you have any questions or want to discuss a new application. We're always happy to help companies building new microfluidic tech. If you're interested in more design resources, enter your email at the bottom of our homepage to get a notification whenever we add new content. Thanks for watching our tutorial on how to design a microfluidic device using SolidWorks.